Hi guys, assalamu alaikum. I hope you are all well and having a good day. So today we'll be solving the last physics Unit-6 paper for the January 2025 candidates, which will be helpful for the May 25, Jan 26 and October 25 candidates as well. So without wasting any more time, let's get started. Before starting, I just want to say one thing. While solving this paper, whenever a difficult question arrived, I wrote them down at first, and then later on what you can do is you can wait for my explanation. I have written everything and then later on I explained, okay, the difficult parts. So don't scroll up or get out of the video right after looking at that I'm not explaining. Yeah, I have explained everything, but after writing the difficult things I have explained. So make sure you are watching the whole video so that you get the pretty good hold of this paper, because the January 2025 paper will be quite a bit like this paper. So let's get started and solve the October 2024 Physics Unit 6 question paper. Now, in the first question, they have said, a student investigated how the current in a diode varied with the temperature of the diode. Student varied the temperature of the diode from room temperature 0 degrees Celsius from room temperature to 100 degrees Celsius, means 25 degrees Celsius, 20 degrees Celsius, using the apparatus shown. Identify one health and safety issue, how it should be dealt with. Okay, let's look at the scenario first. Here it is, the water is a hot plate and the water, and there is a beaker. So first thing that comes to my mind is this water will be really hot, right? This beaker will be hot as well. This beaker and the water will be hot. So let's write it down. The beaker will be hot as it is 100 degrees Celsius. As the beaker will be hot, it should be dealt with caution. So what will be the way we will deal it? We will use tongs. We will use tongs or insulated gloves to move the beaker. Okay, now let's move forward to the next question. In the next question, they have said, the student connected the diode in the circuit shown. He used the ammeter to measure the current as he varied the temperature. Explain why the student correct to include a variable resistor in the circuit. So why did he add a variable resistor in the circuit? This is the question, right? First of all, what we can see in the question is the student connected a diode in the circuit. Student connected a diode. Here is the diode. The student connected a diode. So what is this diode doing? The student connected the diode and varied the temperature. He connected the diode and then varied the temperature to measure the current. This is the first thing. He connected a diode and then varied the temperature to measure the current. When the temperature of the diode changes, he is varying the temperature, right? So varying the temperature means the temperature of this diode will change. When the temperature changes, the resistance will also change. The resistance also changes, and when the resistance changes, it will cause the current in the circuit to change as well. And in order to change the current in the circuit, it will change the potential difference across this diode, and this potential difference across the current will not be constant. Because to change the current, the potential difference must also change, because the resistance is changing as the temperature is changing in the diode. So I am explaining it again. The student has connected a diode in the circuit. And varied its temperature to measure the current. When the temperature of the diode changes, as he is varying the temperature, when the temperature of the diode changes, its resistance also changes, which can cause the current in the circuit to change. How the current will change? If the potential difference is not kept constant. So in order to stop this thing to happen, for the current to change, and he has also added a variable resistor in the circuit. So what this variable resistor will do? The variable resistor is used to adjust the total resistance in the circuit. The variable resistor is been used to adjust the total resistance in the circuit. This variable resistor ensures the potential difference, the PD, is constant. But if the variable resistor wasn't there, the current would have changed and the PD wouldn't have been constant. So as we have added a variable resistor, now the PD will be constant, and as the PD across the diode, this PD across the diode will be constant, even as the resistance of the diode changes with temperature. As the temperature change, the resistance will change. But if the variable resistor wasn't there, then the PD across the diode would have changed. But as we have added a variable resistor, when the temperature changes, the resistance will also change, but the PD across the diode will remain constant, which would normally this will happen. Now, as we have added a variable resistor, when the temperature changes, the resistance of the diode could decrease. When the temperature changes, the resistance decreases, which would have normally increased the current, but as we are using a variable resistor, the student can adjust the current to maintain a constant voltage across the diode. He can maintain the current to maintain a constant voltage across the diode, allowing them to study the current temperature relationship without other variables affecting it. So now, as the voltage is constant, now we can study the current temperature relationship. We can study the current temperature relationship. In short, if I make you guys understand even, the variable resistor right here is there to control the current and prevent change in resistance. It is there to control the current and prevent change in resistance due to the change in temperature from altering voltage across the diode. Okay, so I have made you guys understand. Now what we will do is we will write the 2 points. Why we are using the variable resistor? To ensure the potential difference across the diode is constant. This is the first thing. The second thing is why the PD across the resistance needs to be constant. As the resistance decreases or as the resistance changes with temperature. We don't need to write about the changes. Resistance of diode, please mention that resistance of diode changes with temperature, or you can also mention circuit. So now let's move forward to the next part. The next part, what they have said is, the student predicted the variation of current with temperature would be linear from 0 to 100 degree Celsius. He recorded the following data to plot a graph against temperature. They have asked us whether the unit for current in the table is correct for the data. So first of all, let's figure out the current. We know current is equals to voltage divided by resistance. We will take this 6 volt and we will add these two resistance, because these two resistance are acting on the circuit, right? Both of them are acting. So we have to add both the resistance. We have to add the whole resistance that is acting on the circuit, which is 1100. So 6 volt divided by 1100. The answer will be 5.5 into 10 to the power minus 3 ampere. So this is our correct answer. Now we have to draw a conclusion. The conclusion will be that this calculated current is corresponding, it is very slow, right? It is way smaller than this value, because they are in ampere and it is in 10 to the power minus 3 ampere. So as we can say, the student predicted the variation of current with temperature that it would be linear. But as our current value is way smaller, than the current values in the data, we can say the calculated lead current is way smaller than the data value due to the non-linear behavior of the diode with the temperature. We can say there is a non-linear behavior. Now let's move forward to the next question, the final question of this question number 1. They have said, give 2 reasons why this data cannot be used to test the student's prediction. Why? Because as you can say, he only calculated for 3 temperature values. The values shouldn't be a much more data. We need more data. This is not enough data. Only 3 values are not enough. At least 5 or 6 values are needed. We can say there are not enough sets of data to draw a graph. This is our first point. The second point will be this temperature variation, the variation of temperature, the way he varied the temperature was really small. The variation should have been bigger. The range of temperature is too small. We can mention the range of temperature is too small. So yeah, we're done with the question number 1. Now let's move forward to the question number 2. Actually, I have done the question number 2 before question number 1. So let's watch the brief video. Okay, so moving on to the question number 3. A student investigated the free oscillations of a mass spring system using the apparatus shown. The student is placed the mass downwards, okay, and allowed the mass to oscillate. She used a stopwatch to determine the time taken for the mass to complete 5 oscillations. These are the 5 oscillation times. Okay, 1, 2, 3, 4. Determine the mean value of the period T. So she has asked to find the mean value of period T. So this is 5T. We know 5T is equals to 7.69 plus 7.58 plus 7.43 plus 7.51 divided by 1, 2, 3, 4. There are 4 values, so divided by 4 is equals to 7.55 seconds. This is the 7.55 seconds. Now she has asked us to find the value of T. We know 5T is equals to 7.55 seconds. So T is equals to 7.55 divided by 5 seconds, which is equals to 1.51 seconds. So we are done with value, finding out the T. Now she has asked us to determine the percentage uncertainty. We know they didn't give us the uncertainty, so we have to calculate using half range. Okay, we have to calculate using half range. So percentage uncertainty is equals to half range divided by average measured value into 100%. We know average measured value is 7.55. So 7.55, the upper one will be half range, means range divided by 2. The range is, the bigger value is 7.69 and the smaller value is 7.43. So 7.69 minus 7.43, this gives us the range. Now half range means divided by 2 into 100%. So the overall answer will be 1.7%. Our correct answer is 1.7%. Now moving on to the next part of the question, they have said the student measured the time for multiple oscillations and calculate the mean. Okay, this is one thing that he has done. Determine 3 other techniques. So they have asked us about the 3 other techniques. The 3 other techniques will be using a timing marker at the center of the oscillation. Okay, she has to use a timing marker at the center of the oscillation. And the other one will be before she starts the timer, she should let the mass to settle down, because it will be the oscillation to settle down, because it will be oscillating at a very high frequency at first. So the timer should start after the oscillations has settled down. And the third thing will be, she will be giving a displacement, right? She will be giving a displacement. So the given displacement should be small. She should give a small displacement. Okay, so let's draw them down right here. First point will be and the third point will be use a small displacement. So we are done with all the 3 points. Now moving forward, they have said the student modified the apparatus damped oscillation of the mass spring. She placed a circular piece of card between the mass to act as a damper. Okay, so the greater work needs to be done. So in terms of removing the energy from the system, this is what damping means. The amplitude A of the damped oscillation with the number n oscillation is done by this. A is the initial amplitude and lambda is a constant. So what they have asked us to do is devise a method to determine the time taken for A to decrease to half its initial value. So regarding the time taken to half, use of a suitable graph. Okay, very good. So they have said use a suitable graph. So let's learn them. First of all, we can do is we can learn this expression. Ln A is equals to ln A naught minus lambda n, right? This is what it will come when you learn them, because ln E is equals to 0, or ln E is equals to 1 actually. So minus lambda n. So we can say y is equals to mx plus c, where minus lambda is our gradient, n is our x-axis, and ln A is our y-axis. So we have to draw a graph of n and ln A. Okay, and we have to calculate the gradient using minus lambda. This is the point. Okay, so first of all, as we have to draw a graph of ln A against n, so we have to measure the A as well, right? We have to measure amplitude to draw the graph. So using what we will measure the amplitude, we will use the meter rule to measure the amplitude. Okay, we have to use a meter rule to measure the amplitude. So okay, so as we have measured the amplitude, we have to do some techniques while measuring the amplitude. Okay, so we have to be sure that the meter rule is completely vertical, right? So that in order to become sure that the meter rule is completely vertical while measuring the amplitude, we have to use a set square so that the meter rule is completely vertical. So use a set square to ensure meter rule is vertical. Now we have to record the value of amplitude, right? To what? We have to record the value of amplitude at a known value of n. We have to see what is the value of amplitude at a known value of n. Let's say n is 2. So when n is 2, what is the value of amplitude? So at that way, we have to calculate the amplitude. So we have to write record the amplitude A at a known value of n. Let's say we know the known value of n is 2. So at n is 2, what is the value of amplitude? We have to record that. And we cannot record for one value. We have to record this thing for at least 5 sets of data. For the 5 different values of n, we have to record the value of A. Let's say when n is equals to 3, what is the value of A? When n is equals to 4, what is the value of A? Like this, we have to calculate for 5 different values of n. We have to record A for 5 different values of n. Record at least for 5 different values of n. Our first thing, now we can plot a graph. Plot a graph of ln A against n. Now after plotting, we can figure out the gradient as minus lambda n. Calculate the gradient minus lambda and use ln 2 by minus lambda n is equals to, right, because n is our half time. By this we will get our half-life, and then we have to multiply it with our time period. Okay, so we are basically done. So basically, if I make you guys understand why I did write them, n is equals to ln 2 by lambda, is because n means the number of oscillations it takes for the amplitude to half. The number of oscillations it takes for the amplitude to half. The number of oscillations is equals to n2 by lambda. And why did I multiply with the time period? If we've multiplied the number of oscillations by amplitude, because if the number of oscillations by time period, we get the total time it takes for the amplitude to decrease to half. By multiplying the number of oscillations by time for one oscillation. Time period means time for one oscillation. This is the number of oscillations when A has decreased to half its initial value. So we have got our number of oscillations. Number of oscillations multiplied by the time taken for oscillation give us the total time taken. Okay, they have asked us to find the time taken, so we will get the total time taken by this. If I make you guys understand again, we have used the value of n, this n, which is the number of oscillation it takes for the amplitude to half, because it tells us how many oscillations are needed for the amplitude to reach its half value. Now to find the total time, for this to happen, we multiply n by time period. The time period is the time it takes for one full oscillation. It is the time taken for one full oscillation. So multiplying the time taken for one full oscillation divided by the number of oscillations give us total time taken. And this n is as half-life formula, which is ln 2 by lambda, because at half-life how many number of oscillations are there. That's why we have used the half-life formula for n, nothing else. Hi guys, so let's start solving this question number 3 right now. In the question number 3, they have said the luminosity of a main sequence star varies with the mass m of the star. Okay, the relationship between L and m is given by this, where L is the luminosity, m is the mass, and r is the constant. Okay, explain how a graph of log L against log m can be used to determine the value of r. So let's take log into this graph. So here they have written log L is equals to, as there is a multiplication sign right here between L naught and m divided by m naught, we can add a positive right here. It will be log L, the multiplication will become positive, and here it will be, this r will come in the front, r log m divided by m naught. So this is the formula that we have derived using the log. Now we know this is comparable to y is equals to mx plus c. Here this is our mx and this is our y-intercept. So here we can say y is equals to mx plus c, where this r is the gradient. make sure to write this word, otherwise you will lose 1 mark. So now let's move forward to this question. They have said the data for 6 main sequence star is given below in the table. Plot a graph of log L against log M. So we have to put log into, when they said log L against log M, we can say the first one is going to be our y-axis and this is going to be on our x-axis. Okay, so log L. So these L values needs to be taken into log 31,200, log 31,200. We have to write it like this: log M divided by M naught and log L into 10 to the power 35 watt. This is how we will to write. So log 6.5 is 0.813, this is 0.505, this is 0.230, this is minus 0.032, this is minus 0.108, this is minus 0.328. Here it's 4.494, 3.483, 2.371, 1.483, 1.210 and 0.386. So this is how we have written all of them. So let's go and draw this graph. They have given 6 marks for drawing this graph. Use the additional columns for your process data. Do not convert the values of L from 1035 to watt. Okay, so you have to take it in 1035 value. So if we have a look at them, if we have a look at these points right here, you can say it's 0.8. The smallest value is this, the biggest value is 0.8, which decreases to minus 0.3. So from 0.8 to minus 0.3, from 0.8 to minus 0.3. So it's a difference of 11 boxes. It's a difference of 11 boxes, and you have to take one thing that I want to mention is scaling should be of 1 to 5. These are the 3 ways you can scale. You cannot scale with value of 3 or 4. I'm going to show how I'm going to scale these values. Come on, let's go into the graph. Here we need 11 boxes. What do we have? 1, 2, 3, 4, 5, 6, 7. Actually, log M is our y, is our x-axis. Sorry, my bad. This is our x-axis. So let's take it from here. 1, 2, 3, 4, 5, 6, 7, 8. This is the 0, 1. So this is 8 boxes. 0, 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 boxes and we need 11 boxes. But we have 11 digits difference between them. So what we have to do is we can take two scaling. We take 2 scaling. We can take a scaling of 2. Okay, so 0.3 is on the negative side and 0.8 is on the positive side. So if we take, let's say, this as our 0 point, this is minus 0.2 and this is minus 0.4. So we are within the range, we are greater than minus 0.3, and in the positive side it's 0.8. So here it is 0.2, here it is 0.4, 0.6, 0.8, and here comes 0.10, 0.12. So yeah, we are within the range, right? As we have taken a scaling of 2. We couldn't have taken a scaling of 1 because taking 1 would have never made this graph this easier. It doesn't have that much boxes, so we cannot take scaling of 1. Now let's take the scaling of this y-axis, where it is This is the x-axis, sorry, my bad. Log m divided by m naught is our x-axis. Yes, we have taken our x-axis. Now let's take our y-axis. This is our y-axis. In the y-axis they have given from 0.3 to 4.4. So there is a huge difference of, the difference is of 4.1. So what we can do is we can take 5 scaling, right? We can take a scaling of 5. If we take a scaling of 5, our y-axis should be from this position. This is our y-axis from where this is our 0, this is 0.50, 1.00, 1.5, 2, 2.5, 3.0, 3.5, 4, 4.5 and 5.0. We have a bigger value of 4.5. So we have crossed all the boxes. We can also take it a little bigger. So now let's map them. We know log L is our y-axis, so we have to write here this log L part, the whole log L 10 to the power 35 watt. And now this is our x-axis. We have to write it right here, log m divided by m naught. So yeah, we're done with writing that as well. Now let's put the points onto the graph. They have given it as, for x-axis when it is 0.8, for y-axis it is 0.49, 0.8 and 4.49. So when it is 0.8, it's 4.49. So we know it's 4.49 is right here. Let's draw it like this. If this is 4, there is 0.5 difference, but 10 boxes. There is a difference of 10 boxes. So we can say every of one of them is 0.05. Each rows is 0.05. So we can say this is 4.1, this is 4.2, this is 4.3, this is 4.4, and we have got a value of 4.4, right? This is a 4.494. So we can take this as 4.45 because this is 4.494 means 4.45. So we are going to take this as our value. Always give crosses. Now let's move forward to the next part. They have said 0.5 and 3.5. We can take as 3.5 because it is greater than 4. It's 4.8. So we can take it as 3.5. 0.5 and 3.5. 0.5 is this. And let's take 3.5. 0.4 and this is our 3.5 value. Then it's 0.2 and 2.4. So we will take this as 2.4. 0.2 and 2.4. This is 0.2 and our 2.4 value is this one, right? If this is 2, this is 2.1, this is 2.2, this is 2.3 and this is 2.4. The two boxes is a 0.1 because 1 is 0.05. Not two boxes, two lines is equals to 0.1. Two lines equals 0.1. because 10 lines is equals to 0.5, so 2 lines is equals to 0.1. Okay, let's remove these boxes that we have drawn. Now here comes the next part. We have done with 3. Now it is minus 0.03. Okay, so if this is 0.1, then minus 0.03 will be, for 0.1 here it is 5 boxes. For 0.1, 5 boxes. Okay, so for 0.03, 0.03. So if this is 0.02, 0.04, 0.05, 0.02, 0.04, 0.06, 0.08, and this is 0.1. So we need for 0.03. So if this is 0.02, it is mix. It is in the middle. It will be in the middle. 0.03 will be in the middle. So let's draw the 0.03 right here. 0.03 for 1.483, so I can take it as 1.5. So for 0.03 it is 1.5. It will be right here, 0.0, 0.02, and this is 0.03 in the middle. So let's draw all those points. Here it will be 0.03. So for 1.5 it will be right in this position. Okay, this was a bit difficult. The next point is 0.1, minus 0.1. So minus 0.1 is right here, and it is 1.2. So for minus 0.1 it's 1.2. We know this is, if this is 1, this is 1.1, and this is 1.2. Okay, the next point is 0.328, so we can take it as 0.3, which is this, and another one is 0.386, so we can take it as 0.4. We can take it as 0.4. So we know this is 0.4. So we are done with taking all the values. Now let's join them together. You should take a bigger box. Okay, should always take a bigger box. Now this is not how the box should be. Let me draw it again. Actually, just give me 1 minute to draw the box in a right way. Yes, so we are basically done with drawing the box. Some of the values will be a bit out of the box. That doesn't matter actually. What you can do is you can extend these crosses. In the mark scheme as well, some of the boxes are a bit away, so you can extend these boxes, not an issue at all. As long as your points are correct, this kind of mistakes doesn't matter. And when you will be drawing using your scale onto the paper, it will be the precision will be much better, because I am drawing it using a pen on the iPad, so it's not that much accurate right here. But whenever you will be drawing, it will be much better, hopefully, inshallah. So now let's move forward and do the next part of the question. In the next part, what they have given is determine the value of R from the graph. So R was our gradient, right? We have seen it before that R was our gradient. So let's go and draw the gradient. bring the gradient. We know this r was our gradient, so let's figure out the gradient from here. Actually this was 4.495. okay, this was 4.495, so we could have taken it as 4.5, then the drawing would have been much better. We can take it as 4.4. we could take it as 4.5. Let's draw it as 4.5 because it was 4.495, 494, so 0.8 and 4.5. so here it will be like this. So yeah, it's matching the box actually. So from the gradient, what we can do is, our biggest value is 4.5 y2, and for y1 we can take this one. We can take this one as well, right? We can take this one, and let's take this 4.5 as our gradient. So the corresponding value of x right here is 0.1, right? 0.8. so we know gradient is equals to y2 minus y1 divided by x2 minus x1. so for y2 it's 4.5, we can write it down as 4.5, divided by, for x2 it's going to be 0.8, right? Yes, 0.8, minus, we have to figure out the y1 value right now. Let's take y1 value as 1, so this is 1, and for y we have to figure out the corresponding x1 value. So for that y1, what was our x1? When y was 1, let's say this is the 1, the graph was right here, right? So it was actually, if this is 0.1, this is if this is 0.2 and this is 0.1, this is 0.14, and it is a minus value, so minus 0.14 minus 0.14. Let's calculate it using a calculator right now. The value will be around 3.60. The value is 3.60. We have calculated the value as 3.60. So the gradient is equals to 3.60, which is within the range. They have given a range of 3.5 to 3.7. So we are basically within the range, not an issue at all. Now let's determine the value of L naught from the graph. Let's determine the value of L naught from the graph. Let's figure out the L naught. Just because we are going to figure out the L naught, we have to look at the thing that we have done. They have access to figure out the value of L naught. So what was our L naught right here? This is our log L naught, right? So log L naught was our y intercept. So they have access to figure out the L naught value right here, y intercept. So right here what we can see is, this was our y intercept, right? This was our y intercept, which was 1.52. This was our 1.52. This is our y intercept, right? Which is our L naught. So we can write it down as log L naught is equals to y intercept is equals to 1.52. Okay, we have taken it as 1.52. So L naught is equals to 10 to the power of 1.57. So now we can figure out the value of L naught. We have to use the calculator right now to figure out the value of L naught. So the value comes as 33.1 for me. and we have to multiply it with 10 to the power 35 because this L is 10 to the power 35 watt. We have to calculate the answer in 10 to the power 35. So the value is 33.1 into 10 to the power 35 watt, which is equals to 3.32 into 10 to the power 36 watt. This is our correct answer. We can give the answer in 3 significant figure or even in 2 significant figure, doesn't matter actually. Now what we have to do is we have to calculate the luminosity of this star. We have calculated the L naught, right? Now we have to calculate the luminosity. Okay, we have to calculate the luminosity. So let's go and figure out the luminosity. So we know L is equals to L naught m divided by m naught to the power of x, right? So which is equals, we know L naught is equals to 33.1 into 10 to the power 35 into, we know m divided by m naught is equals to 33. This was 3.60 for us. So our luminosity value will be 1.3 into 10 to the power 42 watt. Now you guys might have a question, why did I write m divided by m naught as 33? The reason is they have said has a mass of 33 m naught. So we know the formula is m divided by m naught, and m naught is the mass of the sun. So we can write it down like this. If mass is equals to 33 m naught, right? They have given mass is equals to 33 m naught. So we can write it like this, that m divided by m naught is equals to, this mass is 33 m naught, right? So 33 m naught divided by the m naught. So m naught is cross. So our m divided by m naught is only 33. Our m divided by m naught is only 33. That's why I have written this m divided by m naught as 33. And regarding the gradient comes out as 3.60 for me, and it can be between 3.5 to 3.7 for you guys. And as you will be writing or drawing in the graph paper, so your gradient should be much more better. I have shown you guys how to figure out the gradient, though I have drawn using a pen, so my one might not be the correct one, but I have shown you guys how to draw it. So draw it using that way and try to figure out whether your gradient value matches with the mark scheme one, which ranges from 3.5 to 3.7. okay, and don't only look at from my video, try to do this graph by yourself as well, otherwise it will be very difficult for you to do it in the exam day. So it's better to practice before the exam day. Okay, so heading on to the question number 4, they have written, a student made measurements of a wooden meter rule. The width of the meter rule was A and the thickness was B as shown. The student used digital calipers to measure A. So explain one technique he should use to measure A. So this is the A, which is the length, which is the width of A. So one technique should be that they have given 2 marks. So the first technique should be he should repeat at different orientations and calculate a mean value to reduce the effect of random error. We know the technique should be to reduce the random error. So repeat at different places and calculate a mean. The second point should be y, to reduce random errors. And our second point we can write, though this will allow us to get the 2 marks, but I'm going to another point, which is systematic error. To eliminate systematic error, we need to check and correct for 0 error. This is another that you can memorize. So this is our second. Which one you can write? You can write either of them. So here they have given, student clamped the meter rule to a bench. He attached a mass M here at a distance d from the clamp. This is the distance from the clamp. The student displaced the mass vertically and allowed t to oscillate. She measured the time taken for 20 oscillations, where t is the time for 1 oscillation. She repeated the measurement several times. The meter rule is made from wood. The Young modulus of the wood is given by this formula. Okay, stress divided by strain is Young modulus. Explain how increasing d affects the percentage uncertainty in the measurement. So this distance. So when you increase the d, as you increase the d, so basically when you increase this d, this t value will also increase, right? Because this mass, the time taken for this mass to oscillate for this distance from the meter rule is 20t. So if the distance is increased, then the time taken for the oscillation will also increase. So as the t increases, this is our measured value, right? So our measured value will increase. T increase means the measured value increases. So let's write it down first, that as d increases, value of 20t also increase. So the measured value increases. So we know they have talked about the percentage uncertainty. So percentage uncertainty is equals to uncertainty divided by measured value. When the measured value increases, the percentage uncertainty decreases, and the uncertainty remains constant. So we can mention that as well, that uncertainty in 20t remains constant, and percentage uncertainty in 20t decreases. So we are done with the. So now you guys might have a question, why as the t increases, why the d increased? We know the formula, time period is equals to 2 pi into root over L by G. So as the L increases, the time period also increases. That's why as d increases, the 20t also increase. This length is the distance of the meter rule from the clamp. This is the length. Okay, this is the length. So that's why we have used this formula right here. Okay, now let's move forward to the next question. They have said the student recorded the following data. Show that E is about 14 GPE. So we know the formula right here. E is equals to 16 pi squared into m. This 400 into 10 to the power minus, sorry, my bad, 400 into 10 to the power minus 3, because it is in gram, which needs to be converted into kg, into d cube. D is this 0.800, so 0.8 meter to the power of cube, divided by A is this 25.02, which needs to be converted into meter, 25.02 into 10 to the power minus 3, into B cube. B is this 6.17 into 10 to the power minus 3, cube. Okay, so this value when put into calculator, the value will come as 1.43 into 10 to the power 10 Pascal. We have to use Pascal here. Okay, we have to use Pascal. So yeah, we are done with it as well. Now let's move forward to the next part. Okay, let's move forward to the next part. And the next part they have said so that the percentage uncertainty of E is about 5%. They have asked us to find out the percentage uncertainty of E. So we have been asked to find out the percentage uncertainty in E. Okay, so this E includes md cube ab and t squared. Okay, so first of all we can figure out the percentage uncertainty of D. So percentage uncertainty of D is equals to, here they have given us the uncertainty of the measured value. So 0.001 divided by 0.800 into 100. This value will come as 0.125%. Now let's do for the M. Not M actually, let's do for the A value first. Percentage uncertainty in A is equals to this 0.05 divided by 25.02 into 100. So the value will be 0.200%. Now let's figure out for the percentage uncertainty of B. So percentage uncertainty of small b is equals to 0.02 divided by 6.17 into 100. The value will come as 0.324%. Now let's figure out for T. Percentage uncertainty of T is equals to 0.01 divided by 0.62 into 100. So the value will be 1.61%. Now as we have figured out all of them, now let's put them together. Alright, so let's put all the values right now together that we know. The percentage uncertainty of E, here let's write it down here. Percentage uncertainty of E is equals to, we know M, percentage uncertainty of M. Here M and D is in multiplication form, but when we find percentage uncertainty we always add all the values. So percentage uncertainty of M plus percentage uncertainty of D into 3, because here it is cube, so we will multiply it by 3, plus here it is divided, right? All of them are divided, but we will add them, plus percentage uncertainty of A plus 3 into percentage uncertainty of B plus 2 into percentage uncertainty of T. That is how we will do. So let's add them together. Let's add them right here. First of all, the percentage uncertainty of M. The M value will not be added because M is a constant. M is a constant, we will not add the M value. Sorry, my bad. We will not add the M value, we will add the other ones. M is a constant, so we will not add them. Okay, they have then given us the uncertainty of M, and M is a constant, we will not add them. So first of all, the thing that we have to do is 3 into percentage uncertainty of D. So this is 1, so 0.125% into 3 plus the percentage uncertainty of A, so 0.200% plus percentage uncertainty of B will be multiplied by 3, so 0.324 into 3 plus the percentage uncertainty of T into 2 times, 2 into 1.61%. So by adding all of them, the overall value will come as 4.77%, which is the percentage uncertainty of whole E. So we have calculated that effortlessly. Basically what we have to do is, if the power is 3, then this D will be multiplied by 3. If power is 2, then T will be multiplied by 2. If this is 3, V will be multiplied by 3. This is how we have calculated. So now let's move forward to the next part. They have said the value of E for beech wood is this. Deduce whether the material could be made from beech wood. Okay, beech wood is another material. So basically they have given us this as 11.9. Okay, 11.9 GPA. And let's go to the first page. We have calculated this as 1.43, right, which can be said as 14.3 into 10 to the power 9 GPA. No, Pascal. 14.3 into 10 to the power 9. So it's actually 14.1 GPA, right? It is 14.3 GPA. 14.3 GPA. And its percentage uncertainty is 4.77. So we can take the percentage uncertainty as 4.8 also. Let's take percentage uncertainty as 4.8%. Okay. Let's take the percentage uncertainty as 4.8%. Yes. So we have taken the percentage uncertainty as 4.8%. So we know that this is 11.9 GPA for Beechwood, and this 14.3 GPA was for another material of wood. This is for wood. So they have asked the value of E for Beechwood is this. Deduce whether the material could be wood for Beechwood. So for Beechwood, we have to calculate the lower limit. Of Young modulus. Let's figure out the lower limit of Young modulus. Let's figure out the lower limit of wood and see whether that lower limit is smaller or greater than this Young modulus of Beechwood. If that is smaller, then we can say that if it is greater, then we can say if the lower limit of wood is smaller than Beechwood, then Beechwood can be used. So let's figure out the lower limit of Young modulus, which is equals to, we know, 14.3 minus 14.3 into the percentage uncertainty, which is 4.8 divided by 100. So the value will come as 13.6 GPA. As the value has come as 13.6 GPA, which is greater than 11.9, so the Young modulus of Beechwood is less than, we can write the Young modulus of this Beechwood, which is 11.9. Beechwood is smaller than the lower limit of Young modulus. So the material is not made up of wood. If this lower limit of Young modulus was smaller than the Young modulus of Beechwood, then yes, it would have been made up of wood. As the lower limit of Young modulus of wood is greater than the Young modulus of Beechwood, that it is not made up of Beechwood. So the material is not made up of Beechwood. So basically we have completed the whole question number 4. Now let's move. We have done with the paper as well. So